All right, so tonight we're going to be looking at 5.3, which is talking about bisectors in triangles. So today in class what we did is we looked at angle bisectors and perpendicular bisectors in just angles and segments and what happens then. So what we're going to be doing tonight is looking at angle bisectors and perpendicular bisectors in triangles. And we'll find that some pretty neat things happen with that. So the first thing before we get into that is I need to define a few words for you. The first one is concurrent. What concurrent means is three or more lines that intersect at one point. So three or more lines that intersect at one point. So it's no big deal for two lines to intersect at a point. Obviously that's going to happen unless they're parallel. But for three to intersect at the same spot, that's pretty neat. So here, if we were to label these line A, line B, and line C, A, B, and C would be concurrent lines. They all intersect at one point with each other. All right, so next we need to define the point of concurrency. All the point of concurrency is it's the point where concurrent lines meet. So it's just that point that they all touch. That is your point of concurrency. So here in line A, B, and C that I just drew, this point here, we'll call it D, would be our point of concurrency. So for example here, it'd be point D. That is a point of concurrency. So what I want to do now is look at concurrency of perpendicular bisectors. So we've got this triangle ABC here. So what I'm going to do now in each one is I'm going to draw a perpendicular bisector of each side. So first I want to look at side AB. So when I do that, I am going to guesstimate here about what the midpoint is and draw its perpendicular bisector. So I'm going to say that its perpendicular bisector is about right there. Okay, so we'll call that line L. Line L is the perpendicular bisector of side AB. It's pretty close. All right, so now let me perpendicularly bisect AC. So if we were going to do that, that perpendicular bisector would be about here. So that's another perpendicular bisector. It bisects this side AC, and we'll call it M. And then the last one I'm going to do is do the perpendicular bisector of that third side. So there is about the perpendicular bisector of the third side. We'll call that line N. So it's perpendicular to side BC, and it also bisects it. So you can see that all three of those perpendicular bisectors meet in one point. Meet in this point here. We'll call that point P. So perpendicular bisectors have a point of concurrency. They are always going to intersect each other. Those three perpendicular bisectors will always intersect at one spot, which is pretty neat. And we call that spot the circumcenter. So here, point P is called the circumcenter of the triangle. And the circumcenter is just the point of concurrency for perpendicular bisectors. And we'll talk about in a second why that's called circumcenter. It's the point of concurrency for perpendicular bisectors. That is the circumcenter. So now we're getting into all these names. So that's where it's really important to write all this down so that you know the difference between a circumcenter and what we're going to learn about next. And then we'll learn about more on Monday. So we're going to have to be able to really keep those straight. So now something really special happens when you have perpendicular bisectors of a triangle. If I were to draw segments from that circumcenter to each vertex of that triangle, you would find that they are all the same length. And here, of course, everything's not drawn to scale. I'm not perfect. I can't draw everything exactly right. But each one of those segments should be the same length. Okay, and if you look in your book, they can show you an example of where everything is exactly the same. So here, that lets us know that points from the circumcenter to each vertex of the triangle are congruent. They are the same length. So for instance, if I wanted to write out just a little theorem about the concurrency of perpendicular bisectors, and we can add theorem onto that word, so we've got it all straight. I could say that the perpendicular bisectors of a triangle are concurrent, meaning they all meet, at a point called the circumcenter equidistant from the vertices. So from circumcenter to vertex, those segments are all congruent. Any segment that goes from circumcenter to vertex is going to be congruent. So let's write that out specifically for our example. So that means that PA is congruent to PB is congruent to PC. Okay, that circumcenter creates congruent segments. So why is it called a circumcenter? Well, it's actually called a circumcenter because it is the center of a circle that circumscribes the triangle. Okay, so that just means that it's the center of a circle that contains the triangle. So, which now that makes sense that each of those red segments from circumcenter to vertex of the triangle would be congruent because they're all radii of that circle, the circle that circumscribes the triangle. So of course those segments are going to be congruent. So right here I just want to talk about where the circumcenter of a triangle is going to lie. And that's going to be different depending on what kind of triangle it is. If it is an acute triangle, the circumcenter will always be inside the triangle. Always, always, always lie inside. If it is a right triangle, the circumcenter will be on the hypotenuse of the triangle. And then if it is obtuse, it will lie outside of the triangle. It will meet out there. And if you try drawing 3 of each type of triangle and doing the perpendicular bisectors of each, you will see that that's true. Right triangle would be right on that hypotenuse, obtuse will always be outside, which is pretty neat. So next I want to look at finding the circumcenter of a triangle. Given coordinates of a triangle, can I locate the exact circumcenter of that triangle. So here we have triangle ABC, so I'm going to go ahead and graph that. A is at 2, 7. That's about right here. B is at 10, 7. So that's right here. And C is at 10, 3. So right here. So now I'm going to connect each side of that triangle. All right, so we've got triangle ABC. We want to locate the circumcenter of that triangle. So there are a few steps that we have to take in order to be able to do this. If we can draw two perpendicular bisectors and find their point of intersection, then we know exactly where that circumcenter is going to be. So you can see here, if you look, I've got a horizontal. Here I've got this horizontal line, and I've got a vertical line. So it's going to be easiest for me to find the perpendicular bisectors of those. So first of all, I need to find the midpoint. Of AB. All right, so let's find the midpoint of AB. To do that, we have to use midpoint formula, which you should all know what that is, but I'm just going to go ahead and work it out. So that'd be 10 plus 2 over 2, and then 7 plus 7 over 2. So if you can complete that, the midpoint of AB would be 6, 7. So I'm going to go ahead and graph that. So that would be right about here. We'll call that point D. That's the midpoint of AB. All right. So next, after we do that, I want to write the equation of a line that's perpendicular to AB that goes through point B. And we know that a line perpendicular to a horizontal line is just going to be a vertical line. So that's going to be the equation x equals something. So since in our midpoint x is 6, that's going to be the equation x equals 6. That will be our line that is perpendicular to our given one and goes through the midpoint of that. So now I'm going to draw that line. So here is that perpendicular bisector. So I will call that line L. I'll just extend that up a little bit. So that is the equation for line L. So now we've got one step done. The next step is to find the midpoint of one of those other sides of the triangle, and then to write the equation of a line that is perpendicular to it at its midpoint. All right, so if we look at line BC, again, that's going to be the easiest one for us because it is a vertical line. So we want to find the midpoint of BC. All right, so to do that, we're just going to plug in that information. So that would be 10 plus 10 over 2, comma, 7 plus 3 over 2. So that point will be the point 10, 5. So if I were to graph that, the point 10, 5 would be right here. And so the equation of a line perpendicular to it, since it's vertical, it's going to be perpendicular to a horizontal line. So that means it's going to be the equation y equals, and here y equals 5. So that's the equation of a line that is perpendicular to that one. So I can graph that line right here. So we will call that, extend that out a little bit, we'll call that line M. So the place where M and L meet, where they intersect each other, that's going to be the circumcenter of your triangle. So here, the point of intersection is your circumcenter. And here we had a right triangle, so it made it a little bit easier for us. If it wouldn't be a right triangle, it'd be slightly harder. So here, the place where those two lines meet each other, where they intersect, you can see that point. It's right here. That would be the point 6, 5. So they intersect at the point 6, 5. Therefore, the circumcenter of this triangle is the point 6, 5. And you can see that that really is true when they're all nice and graphed. Okay? So that's all we're going to do for today. We're not going to get into the concurrency for angle bisectors. We'll talk about that in class tomorrow, as well as doing a lot of these problems like this where we're finding the circumcenter of triangles. See you then.